Okay, so hello, Zheng. I'm from Intel. So I've been a software developer working on the match interface. So the match interface is basically so the talk is about match interface and how can we integrate match interface into OVS to do OVS accelerations. Okay, so this is a legal disclaimer. So the main points are a match interface overview. So I'm going to talk about what is match interface and what it looks like and how to use it. And then the usage scenarios for a match interface and the usage models of match interface and some examples of how you can integrate match interface into OVS and how you can accelerate OVS and stuff. And then I'm going to talk about the integration point from match interface into OVS, and then there's a summary. Okay, so what is match interface? So match interface is a generic match action pipeline runtime. So a pipeline contains tables, and they interconnect together. So tables have rules, and each rules have matches, which basically match the match conditions on the packets, like packet headers, ingress ports, metadata, that kind of stuff. And actions are actions that the pipeline can perform on the packets. For example, you can count the packets, drop the packets, you can sample mirror the packets, you can forward packets to different ports, you can do packet modifications. And configuration is the configuration of the pipeline. So it has table attributes. For example, some tables you can say you want it to have priority or not on the table. It has port attributes and port stats and stuff like that. So it's the configuration of the pipeline. And you have headers, which is basically the structure of the packet. It's the protocol header. And the pipeline can be defined in a language such as P4. So if you define a packet processing pipeline with P4, and then you can have a tool that runs on the P4 spec, and then it can generate C headers and skeleton code to be used in match interface. Okay, so on the left is basically the basic functions provided by match interface. So you have get header, which basically shows you all the headers that match interface, all the underlying pipelines understand about the packets, the packet headers, and then you have header graphs that basically says Ethernet header followed by IP headers, maybe, and then followed by L4 headers and stuff. And then you can do get tables, so it shows you all the tables and of the pipeline. And then you can do get header graph, which basically shows you the interconnect of the tables in your pipeline. And then you have get actions, which basically tells you the parameters of the actions. And for some tables, you can create subtables. For example, for a TCAM table, you can subdivide it into multiple subtables, each one with different capabilities, different sizes, so you can optimize your TCAM that way. And then destroy tables is basically just destroy the table that you create. And then you can have set entries, get entries, and clear entries, which basically programs that arose into your table, and you can get the stats and the state of the entry, and then you can delete that entry from the table. So how do you use it? So first, you use get header, and you get table graph, and you understand the capability of your pipeline. And once you does that, for every table, you can do a get table, and then it shows you what are the matches, basically the capabilities of that table, what are the matches and what are the actions it supports, and how big that table is. So the size of basically how many entries you can program in that table. And then for each actions, you can get the parameters, like for example, for a tunnel push action, you can specify, for example, the other headers, like the IP address and stuff like that, right? So in addition, if the tables have capabilities for you to subdivide them to optimize the usage, then you can create tables. So once you create the tables, and then if you do a get table or get table graphs, and it shows you not only the tables that's fixed in the pipeline, but also the tables that you created and how it fits into the pipeline with the graph. So after you've done all of these, then you can program the entries into your tables by using set entries, and then you can do a get entry to get what are the entries in your tables, and then you can delete the entries from the table. Okay, so usage scenarios. So a couple of scenarios. These are scenarios actually Dan talked about just earlier. So you can do an infrastructure scenario where, so you have the programmable pipeline, then you have a spec that goes into the pipeline to configure the pipeline. And then you can use OVS with match interface integration to program rules into your pipeline. And then the pipeline can forward packets, process packets, and forward packets between your virtual ports, between the VMs. And then you have the second scenario where it's VNF, where so you have a application-specific pipeline where you use match interface. You can program the programmable pipeline, and then the pipeline can process and forward packets to different queues to fully utilize your VNFs. Right. Okay, so the usage model. So for the first scenario, what you can do is you can do feature accelerations. For example, you can do TCAM pre-classify, and then you can do, for example, VTAP accelerations. So I'll talk about these later. And then the pipeline can steer the packet to and from the vPorts. So you do feature acceleration, and then you can steer packets to and from the vPorts. So for the second scenario, it's so your VNF is in your VM or your container, and then you can still do your feature accelerations. For example, you can still do pre-classify, TCAM pre-classify. You can do tunnel encap, decap, and then the pipeline can steer the packets to and from the queues. Okay, so here's an example. So you have OVS. So even though OVS is in two boxes, but it's really the same instance of OVS. So it's just easier to see it, as linearly. So so here you have VXLAN encapsulated packets coming into OVS, and then OVS with the acceleration integration can do the feature accelerations. For example, it can do wildcard matches in the programmable pipeline. It can give you metadata as a result of your wildcard matches, and then you can do tunnel encap. In this case, tap encap in your pipeline. And then you can also do other things. You can count the packets. You can mirror or sample the packet to do monitoring and stuff. Then you can do policing. And then the packets get steered from the pipeline into the vPort in scenario 1, or into the queues of a vPort in scenario 2, where in your VNF, you can run a packet processing engine. In this case, it can be DPDQ. And then in the DPDQ, you can probably do a L3 routing, for example. So in this case, you change the DMAC and egress out of the VNF. gets into OVS again, and OVS can do all those feature acceleration again if you wanted to. And it can also do a port failover in addition to the ingress one. So if you have multiple ports, egress ports, you can program the hardware to do a failover for you instead of doing it in the software. And then you do in this case you do an encap, and then the packet comes out with the encapsulation, the new encapsulated header, and gets routed inside. So this is actually a slide that Gerald talked about earlier. So this is OVS was DPDK NetDev. So I just want to point out in this case, so you can have a match interface integration with DPDK, and then match interface can program the accelerator can be FM 10,000 based Intel NIC, and so you can accelerate DPDK NetDev with match interface. Okay, so feature acceleration for TCAM preprocessor, TCAM pre-classify. So here you have OVS with the match interface integration. So you first do discovery from the match interface to understand the underlying pipeline. And then with OVS rules, you have heuristics where you can say, okay, these OVS flows can be programmed, can be supported by the underlying pipeline. So you use match interface to program into the underlying pipeline. So in this case, you're doing TCAM pre-classify. So you can, for example, program some rules like some flows like wildcard matches and stuff into your TCAM. So packet comes into your host, it hits the rule, then the TCAM gives you a metadata, sets a metadata in your packet descriptor, for example, and then it can steer the packet into OVS. So in this case, an OVS can just look at the metadata to accelerate its processing instead of doing the full flows in software. So in the VNF case, it can steer the packet into VF, into the virtual port, and in the guest, you can run your application-specific pipelines. You can run OVS in it too, and then it will do discovery to understand the pipeline. It will populate rules that can be accelerated into can be accelerated by the pipeline into the guest allocated TCAM. So packet gets steered, and then it hits the guest allocated TCAM, and it may hit the rules, and then it can set the metadata based on the packet, and then forward to the vport where your application running in your VNF can further process the packet. Okay, so for pipeline steering to and from vports. So here you have your underlying pipeline has multiple has physical ports, has vports directly attached. So OVS in this case is acting as a control path, control plane configuration, and also the exception path. And you can see that you have a bunch of VMs, and the virtual ports connects to the VMs. It goes through OVS in the sense that for the accelerated path, OVS doesn't really process the packets. But for the exception case, then OVS does process the packets. So for this type of application, so OVS configures the underlying pipeline with OVS with match integration would configure the pipeline, and then would steer the packet in and out of the VFs. So in this case, so we would use the heuristics based on the use case that we support to basically create heuristics or policies on how what rules can be programmed into the hardware. And then you can read the hardware state back and then keep the software in sync. And then you can age out the rules, or you can evict rules based on usage, or based on the usage of the rules, or the usage of your hardware resource. And then in this case, if the packets that's not being accelerated, it gets forwarded back to OVS, and the OVS can do its software forwarding. In this case. Okay, so for packet steering in and out of VFs or vPorts, we have a new NetDev type called VF, and so in this example, you have an overlay bridge BR1 with a VXLAN port plugin, and then you can plug in a VF into your bridge, into your overlay bridge, and then the VF can, the traffic coming from the VF can be VXLAN encapsulated and goes out. And then, so the requirement for the pipeline for the steering is that there needs to be a direct connections between the vPorts in your pipeline, and then all the OVS rules that applies to the traffic goes in and out of the VMs needs to be applied in the pipeline, and OVS has a representation of that virtual port. In this case, it's the type VF NetDev. So OVS flows copy policy into hardware. So today we support rule sets generated by OpenStack and OpenDaylight. So the VMs connects to the pipeline vPorts, and OVS rules gets pushed into, that applies to that vPort, gets pushed into the underlying pipeline. So anything that cannot be accelerated, the packet forwards back to OVS, and OVS can do its normal software processing. So in this case, so for packets that cannot be handled, OVS can do its, can forward its packet normally to and from the VM, the virtual ports. So this is basically a summary. So what is match interface? It's a generic match action pipeline runtime. It can be the pipeline can be built by a language such as P4, and you can do a discovery. It supports a discovery interface where you can detect the pipelines and its capabilities. And it has an interface for rules to be populated in a table. You can set rules and delete rules and stuff. And we have a preliminary implementation on GitHub, and we're looking to upstream it into Linux in the future. So that's it. Thank you.
So we have some time for questions. If you have a question, please come up to one of the microphones on the side of the room. As a preliminary, we had a couple of different presentations yesterday talk about TTPs and their relationships to pipelines that have generally hardware-based restrictions. Have you thought about any relationship with TTPs here?
No, actually
no.
I haven't.
Oh, that's fine. Okay, just thought you might have. Okay.
Yeah.
So does this pipeline model actually model multiple separate physical interfaces? So that like you can mirror from this vPort to this vPort, but you can't go over to this one on a separate interface. Does it actually contain the set of rules, or is it sort of wide open, and if it fails, it goes through the normal path?
So I guess I don't understand your question.
So if you had two NICs, let's say,
right,
and so obviously you can mirror between vport 1 and vport 0 on this NIC, but you
Right.
can't mirror from this NIC to this NIC over here.
Right, because it's connected through.
Right, so is
PCIe,
that
right?
actually modeled when you get the pipeline information, or
No,
do you just
okay,
go
so
ahead
the
and try
pipeline
and it
model
fails?
only models the NIC, right? This one NIC. It can model individual NICs, but it doesn't modify. It doesn't
Okay, so
model
it's
the
all
network,
per
yeah.
physical device?
Yeah,
Okay.
but it's generic, so you can model any NIC, right? But not a combination of NICs.
Right.
Right.
If we still have time for another question or two, please step up to the mic.
Excuse me. One question for the SRIOV you mentioned. So,
Right.
how is this fit into that scenario? Do you mean SRIOV is already supported with OVS?
Right. So we do have a POC for SRV was VTAP acceleration. Is that your question?
Yeah.
Yes. We do have a POC with OVS integration of SRV with VTAP integration.
But in that case, how would the packets? So, would the packets go still directly through the virtual interface to the VM, or
Right.
does
So
it go
for the
through
accelerated
OVS?
pass, like the fast pass, where the normal packets, it goes entirely through the packet pipeline, so it doesn't really go to the OVS forwarding engine. But for packets that are not handled by the acceleration, for example, ARP or something, then we have a pass where it can be forwarded into OVS.
Got it. Thanks.
Yeah.
All right, we have time for one more.
My question is a little more generic because I didn't understand a few of these presentations from Intel today. So how does this integrate with whatever the latest kernel data plane we have in OVS and OVN with connection tracker and all that? Does it bypass all this? This replaces the kernel stack, or
Right,
is it something
so-
that's integrated with it?
So right now we're integrated with the user space data path.
It doesn't. It's not dependent on how the kernel data path is in the OVS.
Yeah, OVS DPDQ NetDev. Yeah, it's user space.
Okay.
All right, let's thank our speaker one more time.